working?
Yeah.
Well, I think I'd first like to fix a few sign errors or unconventional choices of sign, to put it kindly, from last time, and then go on to discuss something about scalar fields on a lattice, and then something about fermions on a lattice. By the way, Paul Steinhardt, who is one of the developers of inflation, the theory of inflation, is going to be in town the Saturday after exams. He's on a book tour. So I put a notice in the lobby. He's proposed a different model of the early universe in which a universe, there are sort of various versions of his model. One version is that the universe collapses and then re-expands.
A big bounce kind of thing?
Yeah. His latest version is that when it collapses, it doesn't go to zero, it just goes down somewhat, and then expands a great deal more. It goes down somewhat, expands yet more. And whether this is true or not, I don't know. One advantage of bouncing or cyclic universes have over inflation is that they're a quantum correction to a classical solution of Einstein's equations, whereas inflation bases everything on the quantum fluctuation. And that seems to me to be somewhat risky there. So let me go through some of this pure gauge theory again, and with a slightly different notation. So as usual, we have these generators for a compact Lie group. The F's are the structure constants. And now I'm going to define the gauge field matrix as I, a coupling constant, the gauge field, and then the generators like that. And the covariant derivative, the most popular way of defining, let's say that the convention that Kreutz uses and that Weinberg uses is, and also that Peskin uses, is di minus AI, and that is di minus IG, say TB ABI. That's one way of writing it. Now, of course, you can avoid some of these minus signs by putting a minus sign here. And then that may be a nicer notation, but I thought, in as much as Kreutz, Weinberg, and Peskin are all using this notation, I'll stay with that. Then the Faraday tensor is the commutator of two covariant derivatives, and unfortunately now you see this brings in an extra minus sign, so now this looks like minus DI-AJ plus DJ-AI plus AI-AJ, so it looks like that. If we write this in terms of the generators, then what we've got is Fij, and we're looking, say, at the CD matrix element. What we have is minus Bij plus Bj plus Aj, all that CD. And this turns out to be minus Ig to BCD times Di AJB minus DJ AIB plus this commutator, which is IGTB ABI IGTC ACJ, all of that CD, and these, okay, that's where the parentheses go. Okay, now if we work this out, we can just keep this term and then deal with that. And what we get there is we have a minus sign, and then we have minus G squared F. For some reason in my notes I have an E here. And if you think that's silly, so do I, but anyway, that's what I've got. So now this is F B E F A B I A E J T F C D, CD being the CD matrix element there. And there's an I. And so we can regroup this as minus IG T B C D D I AJB. So I'm skipping some steps, which I'll refresh the notes on the web page tonight. Okay, so that's the final form of it. And we can write that as minus IG TBCD FBIJ. So this is the B component of the Faraday tensor. In other words, FBIJ is EI AJB minus DJ AIB plus G FB, and maybe I'll write this as CD, AI AJCD. That's a little bit nicer notation. And the action density for this is minus a quarter FBIJ FIJB. So this is the action in Minkowski space as opposed to Euclidean space. Now, if you take the trace of the square of this Faraday matrix, well, thinking of it in terms of a matrix, in other words, over here, then what you get is you have a minus sign. Well, you've got trace of IG, TB, FB, IJ, and then IG, TC, FC. Here we go with IJ. And this gives you a minus G squared. G is the coupling constant. So you get minus G squared F B IJ, F C IJ, and then the trace of TB, TC. And this is the minus K G squared FBIJ, FBIJ. Now, since we're dealing with a compact group, you can raise or lower the internal indices, and it doesn't make any difference. So this is the action of what's called a pure gauge theory. This is the action density, and you can write it as a trace this way.
Is that a K? Sorry. I was trying to do something else. Is that on the very final term that you've written, is that minus kg squared?
Right. The idea is that the trace of TATB is K delta AB. This K depends upon the representation of the group. And
so that's not necessarily a unique thing. That can be...
The K varies with the representation in order to keep the structure constants invariant. The structure constants are true or are the same for every Lie algebra, every representation of the Lie algebra of a group. But the representations have generators of different sizes, and so we have this K there for that reason. Just to remind you of what's going on here, we have psi prime A of x is here G of x, so AB psi B of x. This is how gauge fields transform under a non-abelian gauge transformation. And what we want is we want the covariant derivative transform correctly. And so this is di minus ai prime of x, g of x, psi of x in matrix notation. So this in matrix notation is psi prime of g psi. And we want this to be g of x di psi of x, which is to say g of x di minus ai of x psi of x. I put in all these of x's to emphasize that the whole point of the gauge theory is that it's invariant under local symmetry, so the element of the gauge group can vary with space-time forms x. To make this work, what we need is dig minus a prime I g should be minus g ai, and that gives us the rule that you've seen before, but it's never hurts to write it down again, it seems to me. And this, the choice of sign that I'm using now, which is the choice that seems to be most conventional. That's how the gauge field matrix transforms under gauge transformation. And so now just to do the how a path-ordered exponential goes. So this is the path-ordered exponential, and I'm just thinking of a very short length of gauge field. And, you know, I put in a coupling constant here. All right, I'll put it in, but then I'm going to take it out because it makes things, I think, too complicated. So this is a very short exponential of a line integral of the connection. So I've got the G0. The 0 indicates that it's, if we were doing lattice gauge, if we are doing a lattice gauge theory, then this is, or flat matter field theory, this is the so-called bare coupling constant, the one that we'll have to adjust to be the physical coupling constant. And path ordering means that the matrices that are early in the path go to the right, and later in the path go to the left. And so in particular, this whole thing under a gauge transformation turns into E, and now we have G of X, G0, AI of X, G inverse of X, plus DIG of X, G inverse of X, and all of that times dxi. So this is, I'm thinking of just a very small, infinitesimally long line integral. And now, ordinarily, if we didn't have path ordering, we'd be confused about this because the derivative of G and G inverse don't, in general, commute. I still got this cold, and so I need
You tried Theraflu? Have you ever tried that? The drink you
the doctor claims I didn't have any, didn't have the flu.
No, that's just what it's called. It's just like a cold medicine kind of thing.
I'm going to run to my office and get a jacket. I'm somehow cold.
He's quite sick last week.
Yeah, he's cold because he's still sick. So they're saying the other end of the card, you have to remember, he has a lot of energy, but he's very old. So when he gets sick, he gets really sick.
I don't have a cold for several weeks in this class.
Normally when
No, geez, you really are.
What?
I said, you really are cold.
Well, I didn't have a simple sweater, so I just, we'll see, maybe he'll get too hot. Anyway, because of the path ordering, we can write this as just the derivative of the logarithm. So this is E to the g of x, g0 ai of x, g inverse of x, plus di of the log of g of x, and all that dxi. And so now, once again, because of the path ordering, we can separate these things and keep them ordered because of the path ordering. So what we have is, we can write it this way, path ordered. First of all, this part with G0 AI, we have here G and G inverse, so we can rewrite this as G of x e to the G0 AI of x, G inverse of x, although I think actually what I really want to do is I want to write this G inverse over here. And then the rest of this is dxi plus, and now I'm simply going to write this as log of g of x plus dxi over 2 minus log g of xi minus dxi over 2. That's all in the exponential, and then altogether a g inverse of x at the end. But now all of this is path ordered, and so the path ordering takes this log of g of x plus dxi over 2 and moves it to the left, and that turns into g of x plus dxi over 2 e to the g0 ai of x dxi. The path ordering takes g of xi minus dxi over 2, moves it to the right where it changes this into g inverse of x minus dxi over 2.
And that's still all path ordered?
Everything, well, and now it's automatically path ordered the way I wrote it.
Okay.
So it's sort of automatically path
We don't need the P anymore?
ordered. Don't need a what?
Just the P, or not? I'm just making sure my notation is consistent. You dropped P.
The twos?
The P up front.
Yeah, I dropped the P because it's already path ordered. It's explicitly path ordered. So now we can imagine what happens. Now we know what happens to a chain of these under, in other words, the path ordered exponential from, say, y to x, u0 ai of x dxi, is then a product, a path-ordered product of e to the g0 ai of x dxi, and when you multiply all these factors of g inverse, g and g inverse on the inside cancel, and what you wind up with is simply g of x path-ordered exponential y to x g0 ai of x dxi g inverse of y. So the whole under a gauge transformation, so I need to put a prime on this. Under gauge transformation, the path ordered exponential of a line integral turns into a g of x, g inverse of y, and then the path ordered exponential. And so in particular, if you have a loop, then you take the trace, you have trace path ordered of an integral of g0 ai of x dxi. This under a gauge transformation, so I'll put a big prime there, will be trace of g of x path ordered exponential loop g0 ai of x g inverse of x or y, whatever it was. In any event, these two cancel because the trace is cyclic, and so this is just the trace of path ordered exponential of g0 ai of x dxi. So that's one of the basic rules, and I wanted to work it out for you this way. I think is that more detailed than what I did last time, and also the signs are more conventional and correct. So now, a Wilson loop is a path ordered exponential of g0 ai of x dxi. And so this is, if we imagine a very small, well, what I want to show is that this is e to the g0. Let us say we're doing a loop in the xy plane. Then this is ay comma, the x derivative of ay minus the y derivative of ax plus g0 ax ay and dx dy, and this then is e to the minus g0 fxy dx dy. And so I did this with I'm using this approximation there are other terms, but they're third order and fourth order in A and B. And since we have A multiplied by dx, that's already an infinitesimal. And so the cubic, the one that's the correction terms of cubic is quartic and so forth. And they're on the third and fourth order in the lattice spacing or in something very, very small. And so there are different ways of doing this demonstration. One way, which we can do is so let me show you two ways, and I'll just sketch the way that I'm not going to do, and then do the way that I did last time, but do it more carefully this time. Suppose x is the center of this small square, and this is of size A. A is called the lattice spacing. And suppose this is the x direction and this is the y direction. So if the fields are, so to speak, imagined to depend upon the point x at the center of the square, then the field here would be ax of, I'll just put in the xy coordinates. It'd be y minus a over 2. And this would be ay at x plus a over 2 y. And then over here we would have ax of x y plus a over 2. And then over here we would have ay of x minus a over 2y. So that's one way of thinking about this. In fact, this is the way Kreutz does it in his book. And let me leave out the G0, the coupling constant, because it just makes things more complicated. Then this Wilson loop would be e to the ax at y minus a over 2, and maybe I'll put in the lattice spacing a. Then this one would be e to the ay x plus a over 2. But here we're going backwards, so this would be e to the minus a x y plus a over 2. Then over here we're also going in the wrong direction, so this would be e to the minus ay x minus a over 2. So maybe I'll continue with this derivation, even though it's not in my notes. So now if we work this out, putting, say, the first two together, we get e to the ax minus a squared over 2 a x comma y, right? Plus a y plus a squared over 2 a y comma x. And then we get plus a squared over 2, the commutator of a of x with a of y. And because we've already got a squared, I'm not keeping track of. I'm referring everything to this point again. And then the product of the last two is minus ax minus a squared over 2 ax comma y. And this one is minus ay minus a squared, well, plus a squared actually. Plus a squared over 2 ay comma x. And then plus a half a squared ax with a y. Now multiplying the two exponentials together, we see that all these terms cancel, and what we have is e to the a squared ay comma x minus ax comma y plus a squared ax ay, and I think I've got that straight, right. And so this is what we call e to the fxy times a squared. What I did last time was to do it with, so maybe I'll just sketch what I did last time with things changed a little bit. It would be e to the ax dx, e to the ay dy plus ay comma x dx dy e to the minus ax dx minus ax comma y dx dy e to the minus ay dy. So this is the way I did it last time, although I'm changing the signs a little bit. In this case, I'm just calling the fields ax, ay at x plus a, ax at y plus a, and ay like that. So this is a simpler representation. And if you multiply those together, what you get is once again e to the ay comma x minus ax comma y plus ax comma ay, all of that dx dy. And so to get to the Wilson action, what one does is take 1 minus the trace of this path-ordered exponential of the loop, and now I'm putting in the coupling constant. And here I've been raising and lowering 4-vector indices, but we're in Euclidean space, so in effect all the signs are positive, and so we don't need to raise or lower anything. And so this is 1 minus the trace of e to the g0 fxy dx dy, and that is then 1 minus, actually there's a typo here, because the ones cancel. So the first term here, of course, is 1. And actually, there's an issue. The question is, what is the dimension of all of these matrices? So in fact, I can't just subtract the trace. I have to subtract 1 over n times the trace. If I subtract 1 over n times the trace, then I get 1 minus 1. And then the next terms are minus 1 over n trace g0 fxy dx dy, and then plus, now let me get this, so let's see, we need to keep track of the i's. the F that we get here in other words, this F that I've been talking about is, so this F here, say ij or xy, let's say xy, this is minus I, the coupling constant, TB, FB, xy. And so if I do this in a couple of steps, we have minus 1 over n trace g0 squared, and it would also be a another minus 1 from the two factors of I, and then you would have TA, TB, FA, FB, XY, XY. And the the minus signs cancel, so these two things cancel. If we're dealing with SON, SUN, or SP2N, all the generators are traceless. So these traces are all gone. So this is just equal to K over N G0 squared FAXY squared A to the fourth, where A is the lattice spacing, so I left out the dx dy squared. So the dx and dy I'm turning into lattice spacings, AX, dx, and the lattice spacing being
But
A.
then the A and the superscript of the Faraday tensor, that's...
Yeah, this has nothing to do, you can call this B.
Okay.
And so the action of a plaquette, in other words, is 1 minus 1 over n times the trace of this thing I call W. And altogether, at least if we get all the factors right, it's G0 squared over 2, FB, say, XY squared, A to the fourth. So, and the full Wilson action then is the sum of this over all the squares of the lattice. And okay, so that's one of the things I wanted to say. Now, let me just say a few initial things about scalar fields. I'm not going to do the whole business, but the basic idea is you represent a 4-vector X as a 4-vector of integers times a lattice spacing. Now, one could have different lattice spacings in different directions, but obviously it's simpler if we just say one lattice spacing. The derivative of a scalar field is then approximated as phi of x plus I hat minus phi of x divided by the lattice spacing A. And so now the Euclidean action would be a sum over all lattice sites and over all four directions I of 1/2 di phi squared. If it's a free theory, it's just plus m squared phi squared of x. And one would multiply this whole thing times a to the 4th. And so this would be a sum of x and I, and this then is 1/2 phi of x plus I hat minus phi of x squared. And then there's an a squared and a to the 4th, so this is just a squared. And then plus a half m squared phi squared of x a to the 4th. And now you can see that since we're summing over everything, you've got phi of x squared, phi of x plus I squared. We're summing over the whole lattice. So this is a term that's very much like this last term. And we can first I want to make things dimensionless. And so what I'm going to do is I'm going to write this as 1/2. I'm going to write MA as M0, so this is dimensionless. So this is M0 squared. And I guess I'm going to write phi this way. So I'm going to write phi A as phi. So then these two things are dimensionless. And that's because the mass and the length are inverse in natural units, and the field has dimensions of mass, and so the field times A is also dimensionless. So now I've written this as something that is purely dimensionless on the right, and moreover, multiplying through by a squared, what we have here is the sum x and I 1/2. We've got phi of x plus I minus phi of I. So now in terms of dimensionless variables, the action looks like that. And A has, in fact, disappeared. So these are all dimensionless variables. And now we can see that this thing comes in 4 times because there are 4 directions here. This comes in 4 times. So it's altogether 8. So we can rewrite this Euclidean action as a sum over lattice sites of lattice sites and directions of 1/2 phi of x plus I hat. Well, actually, it's the dimensionless one. Phi of x, no, this is x, not phi. And there's a minus sign. So this is a minus sign, and it kicks out a 2, so the 1/2 is gone. So let me rewrite this. So it's minus phi of x plus I hat phi of x plus a half 8 plus m0 squared phi squared of x. So that's the action for a Euclidean, for a Hermitian scale field in Euclidean space. And of course here I wrote down everything as if it were a free theory. If it were an interacting theory with, say, an interaction lambda over 4, 5 to the 4th, then it would be a sum over x and I of minus phi of x plus I hat phi of x plus a half 8 plus m0 squared phi squared of x. And then this would be plus lambda over 4 phi to the 4th, because 8 to the 4th times phi would give us the dimensionless one. So that's basically how one does how one sets up a scalar field on a lattice. The scalar field's the easiest thing. And so what you would do is use the Monte Carlo method with this Euclidean action to thermalize your distribution of fields on the lattice that might be 10 to the 4th or 20 to the 4th, depending on how much computer time you want to use. And after a while then you could start computing things. And so you could compute, for example, phi of x, phi of y. This would be a propagator. And this would be, as a functional integral, it would be, let me just go to the dimensionful representation. It would be e to the minus Euclidean action d phi, and then it would be a ratio of path integrals. So it would look like that. Or equivalently, you could redefine d phi to include the denominator. Here on the lattice, you'd use these dimensionless variables, and the thing that you'd use here would be just these dimensionless variables, phi of x and phi of y. And what you'd expect is that this, you would find that this would fall off as something like e to some parameter times the distance between x and y. And then what you do is vary this m0, and since you already don't have any lattice spacing, that you factored that out of the theory. What you can do is imagine that you vary m0 and see what happens to mu. And on a given size lattice, as you vary m0, this mu that you find should approach some constant value, and that would be the mass of the particle in that theory. Now, so so far I've talked about gauge fields and scalars. The one that's very puzzling, of course, is the fermions. And so let me just remind you of how the Grassmann numbers work. And so the basic idea is that if you have a single Grassmann variable, the most general function is a plus b theta, where a and b are complex numbers. And you'd like f of theta d theta, which then would be an integral of a plus b theta d theta. This is going to be a times d theta plus b times theta d theta. And what you really want is for this thing to have nice properties when you shift. And so you want this thing to be the same as that. And in fact, it would be a plus b theta plus zeta d theta. And so this would be a plus b zeta times integral d theta plus b integral theta d theta. So in other words, when you set up the Grassmann business, you only have two integrals that you need to worry about. What's the integral of d theta? What's the integral of theta d theta? Now, if you want to have this shift invariance, then you have to have these two things equal. Well, these two things are automatically equal, but these guys aren't. And so what you say then is integral d theta is 0, and integral theta d theta is 1. You could set it equal to anything, but the convention is to set it equal to 1. And what you the next thing you normally do is you say, well, let's bring in, since we're dealing with things that are complex, let's bring in another variable which we'll call theta star. And so we'll have d theta, integral theta star, d theta star, and we'll also set that equal to 1. And here what we have is a single, or rather two variables, in the sense that the anti-commutator of these two is equal to 1, whereas psi squared and psi dagger squared are both set equal to 0. And so we have then two independent Grassmann variables, and we'll say that they anti-commute with each other. And also that, well, these Grassmann variables anti-commute with all Grassmann variables anti-commute with themselves. And now what we want is, we want to find a reference state. And what we do is we define that as a state psi on some s, and the only thing we require is that s is a state such that psi does not annihilate s. So psi s is some non-zero. On the other hand, psi will annihilate this vacuum state, because that'll be psi squared s, and psi squared is 0. And so now I am sort of out of board space. I can write some of it up here. Let's define a sort of fermionic coherent state as e to the psi dagger theta minus a half theta star theta on this ground state. So remember, the ground state is defined in a kind of arbitrary way. I must say, I'm a little puzzled as to why it is that we're defining the ground state in so completely arbitrary a way. In other words, this is just any state that's not annihilated by that, and then we're building the whole theory upon that. If you happen to see in the literature a better way of doing this, let me know. But this, I think, is standard. So this, we can then expand this exponential, and if we expand the exponential, what we get is 1 plus psi dagger theta minus a half theta star theta on what I'll call it vacuum. Any other terms is 0. The square of this is obviously 0. The square of that is 0. The product of these two is 0. So you only get those terms. And now, maybe I'll use this part of the blackboard. Let's see what psi is acting on theta. Well, it's psi on 1 plus psi dagger theta minus a half theta star theta times the ground state. And, well, psi hitting 1, hitting the ground state, that gives us 0 because of this equation here. Also, psi hitting this would give 0 because psi would anti-commute with the Fermion, with the Grassmann variables. So the only term we have is psi dagger theta 0. And we can rewrite that as 1 minus psi dagger psi times theta times this ground state. On the other hand, all right, hold on a second. But this term annihilates the ground state because psi anti-commutes with theta and psi annihilates the ground state. So this is just theta 0. So what this tells us is that this coherent state deserves its name coherent state because it's an eigenstate of the fermionic annihilation operator. So psi theta is equal to theta theta. We can make a ket out of these variables. So the ket, while it dries, I'll use this. A ket zeta would be 0 times 1 plus zeta star psi minus a half zeta star zeta. So that's just the adjoint of this with theta replaced by zeta. And now we can compute the inner product of zeta with theta. And we just have to write it down, namely, and keep track of all the anti-commutators and all things that are zero. And so this is 1 plus psi dagger theta minus a half theta star theta 0. Boy, it's taking that board a while to dry. Well, one can multiply all of these things out. Maybe I'll just tell you what the answer is, since we have to wait for the board to dry. Zeta theta turns out to be this is in the class notes, so you can, or equivalently, it's in chapter 20 of the book. Zeta star theta minus a half zeta star zeta plus theta star theta. And this looks very much like the coherent state formula for ordinary bosonic coherent states. Now, one of the most important things in the whole theory of path integrals is the Gaussian integral. And it turns out that fermions have Gaussian integrals that are just as nice, if not nicer, than the Gaussian integrals that bosonic fields have. I'm sort of waiting for this board to dry. So let me see if I can start the integral this way. Suppose we have e to the c theta star theta d theta star d theta. By the way, when you work with Grassmann variables, you have to decide, are you going to have a d theta star d theta or d theta star? And it makes a difference of -1 because these things are Grassmann, and so they anti-commute with each other. If we expand this exponential, we see that it's really very simple. It's just 1 plus c theta star theta. There aren't any more terms. And now, we can see that the first term vanishes right away because d theta star is 0 and d theta is 0, integrating. And so the only thing here is c integral theta star theta d theta star d theta. And so we can rewrite that as minus c integral theta star d theta d theta. Well, theta star d theta star, that's 1. And so this is minus c integral theta d theta, and so that's minus c. So the whole business is that the Gaussian integral e to the c theta star theta, d theta star, d theta is just minus c. And that, in fact, is how one treats fermions as path integrals. Basically, you put the fermions in your path integral, you pray that they only occur quadratically so that you just have Gaussian integrals over your fermionic fields. You then replace the fermionic fields with Grassmann fields. Then if they're all Gaussian integrals, you just have things that are as simple as this. And so the basic thing that one does is one integrates out the fermions as basically step one of in path integrals over fermions. Maybe I'll write one more thing here because we're just about out of time. The space of states here is, we can think of as C0 plus D psi dagger 0. So this is our space of states, and we can write the identity operator for this space of states as an integral of outer products of Grassmann coherent states, d theta star, d theta, and we can see that this is 0, 0 plus 1, 1. So I encourage you to do that. That's a nice exercise. So we're just about out of time. I'll stop at this point.